So welcome, everybody. This is the third part of a three-part series that we put together between Magic Communications, Telestream, and Arista. And we're very excited to bring some interesting topics to you as we go through this journey of learning about the SMPTE 2110, the adoption strategy, and what people are thinking about for the future. Please do put your question and answer, or your questions, not necessarily your answers, we'll handle the answers, in the Q&A panel. The chat window we'll use for just general chat, but please do use the Q&A panel. This is a live session. This is for you. Feel free to ask any questions. If you have suggestions, you want us to deep dive into a particular topic, that's great. Again, there are other topics that we covered previously. We are started now, so we're actually going to get started here right now to help you get to the future of what's happening with IP and 2110 and the road to UHD and HDR and high frame rate and all the other coolness. For those that have just joined us for the first time, this is, again, a third part of a three-part series. The first was integrity monitoring, led by Mr. Michael Waitson from Telestream. Thank you very much. By the way, Mr. Waitson is an application engineer from Telestream. To say hi, Mike. Good morning. The second one was unified timing for modern broadcast systems, and that was led by Mr. Lee Whitcomb. And Lee Whitcomb is an architect at Magic Communications. Morning, Lee.
Morning. Good afternoon.
Okay. And then my co-host for today, co-presenter for today, is in this third presentation, Journey to HDR, UHD, 4K, and beyond. And that's with Mr. John Myatt, who's the CTO of Networking Infrastructure at Magic Communications. Morning, John.
Good morning, Robert.
Okay, and for those of you that want the links to the previous slides that we have, the webinars that we have, very detailed information on PTP, architectures and best practices, everything you want to know about PTP and more, as well as the PTP SMPTE ST 2059 best practices that we put together for the IP Oktoberfest. Great information, really well done on all these. Speaking for myself, is I get a lot out of these, putting the information together, and hopefully you get a lot out of this by listening to the information and learning from all the heartache that we've had in the past. So with that, why don't we go ahead and get started here. John, why don't you take us through the journey of going to HDR, high frame rate, UHD, and all these new acronyms that we have?
Sure, glad to. It's a interesting world we've become. You know, back in the 40s and 50s, everything was standard def, it was analog, it was really hard to do, but at least there was only one standard per country. Now, you know, HD, we've had some stability for the last, 20, 30 years, but as we step off this cliff, there's a whole new set of technologies that are confronting us with possibilities. And so we'll talk about dynamic range, standard dynamic range, high dynamic range, wide color gamut, and of course, Ultra HD, and how they affect the workflow of the plant. And separately, we'll look a little bit at the IP infrastructure that goes underneath these things and its technology curves. And you'll see an interesting set of possibilities that are coming toward us as an industry. So we look forward to a fun ride today. That said, there we go. We've been putting video on IP for a long time, and when I put this slide together, I was kind of surprised at how far back it went. The first versions of uncompressed video on IP were back in 2002. And if you recall, in 2002, standard def ruled and HD was new, and gigabit Ethernet was pretty new. 10 gigabit Ethernet was maybe still future, but even then, there was this work going on in the IETF around uncompressed video over IP, and it evolved to become RFC 4175. Now, around the same time, the Pro-MPEG forum, if anybody has enough gray hair to remember the Pro-MPEG forum, then you're the same age as me, worked out a bunch of SDI over IP standards that are another RTP format. And that eventually wound its way through the Video Services Forum and into SMPTE to become SMPTE 2022-6, which of course came on the market in 2012 or so. But 2022-6 was essentially the same as the Pro-MPEG COP4. So there was plenty of product in the pipeline for it. Around that time in the VSF, we started two activities in parallel, one around improvements to 2022-6, in particular, how to interoperate it with AES 67 and other things. And then also a separate activity on breaking the structure and really sending separate essences on separate flows in the IP network. And that was VSF-TR03, which of course evolved to become SMPTE 2110. And if you look at the video part of it, you'll find that it's very much isomorphic to the original RFC 4175, which was a great piece of work. And we didn't really change it very much. We just added ways to describe what the signal is to match modern usages. So where RFC 4175 really just focused on sort of SD and HD, we added language to the SDP to be able to express all these other things that are going on today, because these pixels are not those pixels. They are all different, and you have to describe them properly. Now, along the same ride, the SDI world didn't stand still either, right? And so there was SD SDI, there's HD SDI, there's 3 gig SDI, there was dual link HD SDI that became 3 gig SD SDI, 8 HD SDI. And then of course 6 gig and 12 gig. And each of those was a whole project in SMPTE and got described and beautifully annotated. And those standards, all exist and they're all in use worldwide. 12 gig SDI has a definite place in the ecosystem and it's pretty widely used. There was some preliminary work done on 24 gig SDI, but I'm not sure that it is active in any organization anymore. Someone will correct me if that's wrong, but I believe that work isn't really done anymore. But all to say, the world doesn't stand still, and neither should the technology. So the challenge with SDI is that each of these, 1.5 gig, 3 gig, 6 gig, 12 gig is a slightly different physical layer with different cables and different transceivers and different equalization ranges for the cables. So it makes it a little bit difficult to make a multi-format plant if you really want to support all the things. You have to design for the worst case though. A little bit easier in the IP world, as we'll talk about. So where does that take us? Well, the new kid on the block is Ultra HD. And you might think Ultra HD is just 4K. I go to the store, I buy a 4K set. But it's really a collection of technologies. There's a whole bunch of different technologies that are all in there. And each of them is a response to a constraint of HD. Just like HD was a response to SD, SD was very limited for those who remember it. HD also is a somewhat limited technology. The dynamic range is very limited. The color space is constrained to only slightly better than you could do with a phosphor tube, really. But Ultra HD is a modern set of technologies that's built on the knowledge that we can do better. So it has full, it has obviously double the number of pixels, and people get caught up on that, 3840 by 2160. It's twice as many pixels. Well, it's actually 4 times as many pixels. And really, if you think your math hat on right, it's 8 times as many pixels as 1080i, right? Because then it's 4 times 1080p, squared, all that stuff. That does make it challenging that there's just 8 times as many pixels. But equally, the dynamic range, the expressibility of each of those pixels is much, much better than what we could do in HD. HD, the dynamic range was still limited based on the idea that people would have phosphor displays, even though the reality is that the phosphor displays for HD went away fairly quickly, very early. The underpinnings of the technology were still designed around them and designed around that kind of dynamic range capability. Whereas the high dynamic range, now the OLEDs and the other display technologies can make an incredibly different range of brightnesses from just barely perceptible blacks to sort of poke your eye out hot whites. And likewise, the cameras can capture that, and you really have to have both to make a practical system. So everything about UHD processing is now, how do I get it from the camera to the consumer? The audio world has not stood still either. You know, in standard def, you were lucky to get stereo. That came very late. Most TVs never really supported it properly. In HD, 5.1 was officially supported as part of the ATSC. Many stations broadcast 5.1 audio. But if you sit in your chair and you really try to find that channel separation, you realize, well, a lot of the content is still stereo. Less and less, you know, it's getting better. The next generation audio technologies, as part of the UHD, and the UHD forum is very actively involved in this, really get into the AC4 representational model and the sort of, you know, surround environment, and being able to do much more complicated audio presentations that really go to the, you know, just like being there aspect of television. You know, the whole goal of television is to deliver entertainment, and the audio presentation is a huge part of that entertainment. You know, people will tolerate a less great picture if the audio is really, really good. But the other way around is not true. If you have a great picture, but you got all kinds of garbage in the audio, people will object strongly. So audio is still super important, and there is a whole bunch of work going on in audio, none of which we're going to talk about today beyond this statement. There's also a lot of work going on how to deliver HDR to the home, and there's these different coding approaches, you know, SDR plus HDR layered approaches, direct transmission approaches, and so forth. Not really the focus today, but it's a huge part of finishing the ecosystem. Another one that's just beginning to get some foothold is the high frame rate aspect. You know, the cameras, for the most part, can capture high frame rates. You sometimes have to pay extra to turn that on, but the sensor's capable. And likewise, the displays, if you go shopping for a display, they're all 120, 240 hertz refresh displays. But we're not currently filling the pipeline with that many frames. And so there's a whole set of technologies there that, you know, if the differential consumer presentation value is worth it, there is going to be demand to fill in the pipeline with that frame rate. There's also content aware encoding. You know, there's different approaches to, you know, as always in compression, you can make a lot of trade-offs on how you spend the bits. Now, each of these technologies is somehow a response to what was done in HD, but they're all about consumer entertainment and delivering that sense of immersion. Now, what this means in practice for all of us is that there's a lot of conversion to happen, because people have archives of material that's in HD in standard dynamic range, or standard dynamic range is the polite name for what we've done the last 30 years. And so you'd think, oh, well, you know, there must be an ITU spec that says how to convert SDR to HDR. But the answer is that there is and there isn't. There is a document that says exactly how to convert, depending on which system you're going to. But there's also an artistic element of that conversion that is, how do you actually map the standard dynamic range into the high dynamic range? Do you stretch the whites? Do you compress the blacks? Do you lift it? Do you position it a little differently? And so the ITU spec is sort of like a starting point, but most productions make artistic decisions as well on how they're going to actually position the range and how they're going to actually tone map the highlights. And they do this because it looks good. You can make a better looking production by applying some artistic intent to how you map the standard range into the high dynamic range. But you also have to pay attention to the business driver that at the end of the production, you'd like to create a standard dynamic range to deliver to the viewers. If any of you remember the early days of HD, there was a lot of focus on positioning graphics and things so that you could make a 4:3 center cut for the standard def viewers, because they were still a very large chunk of the audience. Well, we have a similar challenge in producing HDR content that we have to keep an eye on how the down converter, how does the SDR get made at the end of the pipe, and what's that going to look like? Because on the first day, 100% of the audience is still watching through a standard dynamic range delivery system. On the second day, maybe it's 99%, but it will take a while before we even get to a 50% point on this handover from SDR-enabled viewers to HDR-enabled viewers. So there's a lot of art involved in making a beautiful HDR production. And then there's a certain amount of checking and science involved in making sure that you can then create the standard dynamic range from it. And that's the requirement of the business. Early HDR productions were about figuring out how the HDR worked, what shots work, what lighting works, how bright the graphics should appear, because, you know, in traditional standard dynamic range, white was white. But in high dynamic range, white is an escalating sequence of brightness all the way up to staring at the sun. And so you really have to decide where am I positioning the graphic in the great scheme of whiteness? Am I putting it at, you know, what used to be 100 IRE? Am I putting it somewhere lower, somewhere higher? So there's a certain amount of just learning curve to what looks correct in all these artistic choices about high dynamic range production. So early productions like the 2016 HDR work, the 2018 HDR work even, were based around learning how to use HDR artistically and making a final production. But it's really transitioned now into a mainstream element. So if you look at the things done in the last year or two, the Tokyo Olympics and other work, those are much more about how do I make a true dual stream production? How do I make one set of cameras, one set of operators able to create both the HDR and the SDR out of one set of production resources? And that's really getting to the economics of the situation, because, if you think about just the logistics of the production, you can't have two trucks, you can't have two sets of cameras, you can't have two sets of technical directors and everything. You really need it to be one production somehow in order to keep the economics working right. So there's a few different ways to think about how to do the production. Presumably the cameras, the HDR cameras, they capture a tremendous range of light. And then there's a process called grading, where you take that range of light and you either grade it into the high dynamic range system on the top of the screen here, which is maybe a little bit smaller than what the camera actually sensed, but it's right up there. And there's a little bit of artistic input maybe on the color and on the camera shading and so forth to dial in the exact production look. Then on the bottom of the screen, you can kind of see the standard dynamic range production path, which is really more, how do I map all those beautiful highlights down into the standard range and have it look right, which doesn't mean clipping them. It means soft curving them. It means taking the colors that are not expressible in 709 and mapping them into the 709 color range in a way that looks artistically correct. A lot of work has gone into this over the last couple of years. And there's, well-engineered LUTs from BBC, from Comcast, from others that are, the look that's picked for a production sometimes on how those things get mapped. Because then ultimately that standard dynamic range is what goes out to standard dynamic range receivers all over the world. So there's two kinds of technologies here. You can produce HDR, you can produce SDR, but that's two paths. And if you extend that into the production and you say, well, what if I did the whole production workflow as two layers? So each source, I very carefully shade up an HDR version and an SDR version of that, and I make them available to two switchers. I could tandem those switchers. Maybe they're only driven by one TD, but fundamentally, you could take the approach of saying, well, I make both versions of every signal. I take them into these tandem switchers. I make two beautiful productions. That can work, and I think it's been done from time to time, but it is a pretty resource intensive way to do it because you're doing a lot of conversions. You're putting a lot of work on the camera shaders to dynamically create both versions. Ultimately, you still get challenges like the replay. How do you do you record it in HDR, or do you record both replays? That's a bit tedious. And then you still get the problem that there's multiple HDR delivery systems anyway. So even if you produce, say, an HLG, you might want to be distributing in PQ or distributing in Dolby Vision, which is a variation of PQ, or distributing in HDR10, which is a slightly different variation of PQ. So each of those is still a conversion at the end of the workflow anyway. The ultimate goal is to get to an optimized single production where whatever the source is, we create a high dynamic range version for production purposes. So if it's a standard dynamic range camera, you go through some LUT plus stretching up conversion to HDR. If it's an HDR camera, you're good to go. You only have to do normal camera shading. But for every one of those sources, you keep an eye on how is it going to look when it's converted at the end back to standard dynamic range. So you check the SDR conversion. And you can do some of that checking ahead in the design of the LUTs. It's not all game day stuff, although you do have to check it on game day. Then you make one production, and you, at the end, convert that one production into all of your output formats. So this is sort of the grail of how people want to get there. Now, Mike, how are the test tools for this? Are there enough scopes and things that speak HDR and SDR, and is this stuff that people can actually do in practice?
Yeah, so we have a range of different tools that can help define, for instance, the white point, whether it's in 75% HLG or 58% in PQ. We'll put gradicules on the screen to help the user define where that white point is, depending on the gamma that they actually select. And then for the color, they can look at a CIE chart or one of the other sort of vector displays or diamond displays to be able to visualize the red, green, and blue levels to match them all together from the camera through to the transmission of the system. And then we got false color that we can overlay over the top of the picture. And this can be useful to identify regions that are in the shadows, regions that are in the highlights or the specular highlights, and you can identify the regions which are in HDR and the regions which are in SDR. So there's a whole range of tools, and you can find out much more about the HDR tool sets on the Telestream website. Back to you, John.
Oh, okay, thanks. Somehow I expected that might be the answer. The clear thing is that by getting to an optimized single production, you can have a reasonable equipment footprint and make a great HDR production that produces a great SDR production. Because like I mentioned, on the first day, most of the viewers are still getting the production through the SDR delivery. And the look of that production matters. And I think we'll see, much like we did in the early days of HD, that the HDR production, even when converted back to SDR, makes a nice looking SDR production, and that ultimately becomes beneficial even for the viewers who are not getting it in HDR on the first day. Now, there's a couple of tangential issues that come up with HDR. As much as you'd like to use pre-engineered LUTs for these conversions, there's also sometimes a need to have dynamic adjustability. And so as you think about conversion equipment that's doing these, SDR, HDR conversions or HDR, SDR conversions, it's tempting to say, well, I'll just stick the LUT in there and it's good to go. But on game day, you may realize, no, I really wish I could tweak that a little. And so most, good conversion equipment, I'll count ours in that bin sometimes, is able to do a combination of artistic adjustment and also LUT. And then that way you get the best of both worlds, because you can get the engineered graded LUT that does the right mapping and so forth up in the high ranges, but you can also adjust the, the gross color volume, or you can adjust the way that the, brightness maps for a particular shot. And so that combination of being able to apply local production logic, but also the, engineered LUT solutions is a helpful consideration. Another thing to think through is that high dynamic range maps effectively more information in a Shannon information theory sense into that 10-bit space of numbers that we use to represent the luminance and chrominance. Now, in practice, that will affect the bit rate you need for the contribution codecs in order to get the same effective picture quality. And this overlap is something that's a current topic of study, but it is something to plan on, that you may need to spend a few more bits on the contribution link, getting out of the truck, out of the stadium, the backhauls and so forth, when it's HDR, because there'll be more, because there's just more information packed into that same, spectrum of numbers. Now, another thing to think about is, we're talking about HDR here in this webinar that's also about IP. And you might think, oh, well, is this inextricably tied to IP? The answer is no. The SDI system, and 2022-6, which is an extension of SDI, also has some very limited, has 2 bits in there for signaling which HDR format it's in. So you have 2 bits in there that say, is this SDR? Is this HLG? Is it PQ? Is it, I don't know. That's your 4th choice, is I don't know. And so there is a limited ability in there to signal HDR even in SDI, provided that every piece of equipment along the path treats those 2 bits in the VPID correctly. So it can work, and it does work in engineered systems of equipment that's carefully selected. Now, fitting these new formats, just going back to the how many pixels are in the screen, fitting these new formats into IP raises some interesting challenges. In the 10 gig day, when everything was 10 gig Ethernet, which those days are a little bit past, but in the 10 gig Ethernet days, the HD 1080i 720p, you could fit a couple of signals in a 10 gig. It's a nice system. 25 gig lanes on the switches made a big difference, because now, even in 1080p, you could get a reasonable number of signals into an Ethernet link, so you could do clean switching, things like that. The advent now of 100 gig interfaces becoming kind of the standard item on all new switches have a lot of 100 gig support. Now you really have a tremendous number of HD signals. You get like 70 1080i signals in 100 gig E. Equally, you get about 32, 33 1080p signals in a 100 gig Ethernet. So you get a meaningful number of signals in 100 gig, and there's a lot of appliances or things like production switchers that consume a lot of signals can start using these 100 gig interfaces to pull in, a lot of signals. Because if you think about a large production switcher, it has a tremendous appetite for input signals, right? Same with multi-viewers, same with high density processors. But where it really gets interesting is when you start talking about 4K, the UHD 3840 by 2160, 5994 kind of signals. Because there, in 25 gig, you can fit 2. But 100 gig, you start to get 8 to 10, depending on if you're a 50 hertz or a 60 hertz country. And you start seeing some benefit of 400 gig. The 400 gig interfaces now become the high density conduit, 32 UHD signals, 40 UHD signals if you're in a 50 hertz country. So, you do get a huge bump in benefit of the 400 gig transport. And in a minute, we'll talk about the reality of 400 gig, because it's here. It's been here for a while. Now, the other possibility, and this is more than a possibility, it's a reality in certain places, is 8K. Just when we're starting to get used to doing 4K, 8K is the new reality. And the 8K, you kind of need 400 gig to carry a lot of it, but in 100 gig, you can carry 2, and 2 is a good number. And most of the early 8K has caused us to dust off our old friend 211023. Many of the 8K things right now are done with 4 links of UHD, and it's kind of a 2SI of 2SIs, building out that screen. You can send it around as 4 streams. You have to match it up, obviously, and people are doing it. It's not super ideal. The ideal is to get to single stream like we did with UHD. But, for now, 8K as 4 streams is what's happening, in the early work in 8K. And there is, early work going on. There's people building up 8K infrastructures for special events. Now, all to say, as you map all this together, you say, well, is IP actually outperforming SDI in some way? Well, it is, right? So if you think about raw bandwidth, an 1152 square 3 gig SDI router, it's a nice big rack worth of stuff because it's full of connectors. It's got a pretty hefty power budget, comes in around 4 kilowatts if it's got, real processing on those cards. Comparatively, that's anymore a 1RU switch, 32 or 3600 gig ports, 1RU, 500 watts roughly. So that's a huge difference, a whole rack, 1RU. If you get into bigger systems, you start saying, well, how about the current generation of switches that have, up to say 96 or even 128 100 gig ports, or their 400 gig cousins that have, 24 to 32 400 gig ports in a 1RU. That's kind of the equivalent to, a 3200 squared SDI router, which I don't know that anybody ever built a 3200 squared SDI router that was truly non-blocking inside. But here's 1 and 2 RU switches that are doing the equivalent thing. So really the capability has shifted greatly. I mean, at the peak of SDI, it was a complicated technology that was like the hardest thing we could do. Now, if you think about IP technology, these switches, these are the smallest ones that the switch vendors make. This 24 quarter is the smallest 400 gig switch you can buy. And then they make much, much bigger ones, 144, even, much larger on the, thing. There's bigger models literally every year. Even these models, by the time this chart's been online for 6 months, there'll be newer models. So Robert, what's really happening out there? What's, who shrunk the switch and why is this all so different?
John, it's a really good, it's kind of an interesting point about what you can do with the switches. It's also an interesting point of how big is big and where do you start too. So what we're doing, the industry is doing is we're kind of following Moore's law. It's not really equivalent to Moore's law. Like every Christmas, you can buy a laptop that has twice the performance of the prior years, almost like a 2-year cycle. But the reason that that's happening is because the chip dies are getting smaller, much like your Intel and AMD processors are. The ability to actually forward packets are increasing. And what's interesting about that from a media and entertainment perspective, it's following along what's happening with what you were just talking about with getting to 24 gig and beyond, doing not only high frame rate on the lawn, so to speak, on the field, but also having immersive video, immersive audio. I've been working with a lot of VR, virtual reality type of companies. They're taking very high frame rates and putting you inside the field, looking at a particular player, following along with the ball, playing along as if you were on the field, different points of view. And so that allows you now to have different content. But if you look at just the raw, like you were talking about, the performance, the RU size, the wattage and things, everything's decreasing. In fact, if you look at we were just talking about the 38 RU, you've got, some number of SMPs, 36 in this particular case, and some switching fabric, or before that was just the fabric in itself. Now it's an interesting thing to think about this as now I care more about the processing capability than I do about the fabric. But there's other things to think about too in terms of the whole workflow and how the workflow is changing. And so, Lee, you've been doing a lot of things with workflows and even things like validating the workflows and having solution sets that are looking end to end. So what are you seeing from kind of a Moore's law, things adopting and testing from a Magic Communications perspective? Let's see if Lee comes on.
There he is.
Sorry, just clicking that. Sorry.
We're talking about the Moore's law shrink of processing, and you know, it's profoundly affected the IP infrastructure, but equally on the FPGAs and the other stuff that we use to build products, you know, those die shrinks are across the line. I mean, the Xilinx chips are made on the same line that, you know, other people's chips are made on, right? They're all the same kind of technology progression, the same transceiver progression. So we see the same effect, that we can do, you know, more every year with the, you know, bigger / smaller FPGAs, meaning smaller line width, but more gates on a die.
I mean, if you look at, I mean, many years ago, we used to have like a frame sync was one separate card, and you'd have like an input card was a separate card. So to make up a product like that, you used to take several cards because the FPGAs were quite small. Today, with say something like the SMP, you're doing 32 3-gig processing channels and 2 100 gig interfaces in one box. So, I mean, yeah, definitely with Moore's law, as John was saying, the FPGAs are sort of tracking that Moore's law very carefully or closely. And definitely the processing gateways, conversion, multi-viewer products sort of are very sort of tied on that sort of FPGA curve. So yeah, so Moore's law is definitely seeing that work in apply.
You know, it's other thing, Lee, and I'd like to bring in Mr. Waitson as well on this, is the workflows are malleable as well. It's, you know, even though you're buying a particular device for a particular point in time, those things are changing, workflows are changing. And Mike, I'm sure you're seeing this, which is now even what you're doing with your shading, what you're doing with your test and measurement systems, those are also adapting frequently. You have to be more malleable about where you put these things.
Right. So you have to deal with both the SDI side of things and the IP. So our boxes have to deal from an IP side of things and an SDI in all the different formats on both sides of pieces. So that's the first part, is getting the infrastructure to handle both sides. And then having the same kind of tool that the person was used for camera shading in SDI being available for doing that within IP. So you have this mix of the two together.
So IP is kind of interesting in that it's no longer, you know, point in time. It's what do I want to do? And I think that that's one of the differences, is it's no longer about where I'm plugging in, but the personality of the end device and the capabilities.
Yeah, and that's one of the beauties of sort of having this IP infrastructure. Is you add processing nodes to your network. So you're sort of, if you want to do up conversion, you just plug in a device anywhere in the network. It can take the signal to the conversion, put it back into the network or multi-viewers or whatever. So you're just adding the functionality you want, and then you can dynamically build up your workflow instead of having this more traditional A connected to B connected to C kind of workflow. So,
and John, back to what you were talking about originally, which is how do I start? With IP, it allows you to start any which way you want to, whether it's a single input, multiple output, or dual input, dual output. I don't know if you got some thoughts on that, or if that's already been said.
Yeah, I think, you know, we've covered a lot of ground on this topic. I mean, we have a few slides left to go, Robert. We should probably.
Very good. All right, thanks, guys. Appreciate the banter. All right, speaking about how big is big. So just what John was talking about is we've got a lot of processing capability. This happens to be just a 7816. This is the biggest router or switch that we build. If you want something bigger, just talk to us. But in this particular case, and by the way, this is being used in several production facilities. So this is not just vaporware. We're not just making this stuff up. But from a 12G perspective, this is, 3072 by 3072, 3G, 12,672 by 12,672. So this is big. Now, do you have to go this big? No, of course you could go with a chassis that's smaller. But what's interesting from a scale perspective is the ability to do 400 gig in these. 400 gig is not 4 times the cost of 100 gig. It's about twice the cost. But there's several things you want to think about when you're building out a quote 400 gig solution. For example, we were talking to an OP truck vendor here just a couple of weeks ago, and they said, we're tired of dealing with tie lines. We're tired of dealing with 100 gigs. Imagine that. We're tired of dealing with hundreds of gigs. We want to go 400 gig and beyond. Well, this allows you to go to that 400 gig line connection between systems or between facilities or between studios, which gives us that economies of scale for both not only 3G, but also 12G. So now you're able to use the network to be more malleable and get a higher speeds and actually be more malleable in where you actually put your systems. You might have your multi-viewers in one location, for example, and your mixers in that location, and you want to have productions in a different location, but there's a lot of bandwidth coming across. So 400 gig gives you that ability to stretch your facility out, which is really kind of cool. Now, people say, well, what is a 400 gig transceiver? You might hear, from the networking people, an optic or a transceiver. Those kind of two names are interchangeable. Well, there's two standards in 400 gig. There's this optical small form factor pluggable, and then there's this Q SFPDD, which is Q meaning quad, small form factor pluggable, DD double density, which is a lot smaller. Now, there's a lot of processing that's happening on these little chips, these little transceivers. Think about it. You're going electrical to optical to electrical. You're doing all that transition, but you also have other things like EFDAs, EDFAs, as some people call them, and other things that are happening on these as well. These are little mini computers, if you will. So as you add more things onto a die, onto these, they run hotter. The farther that you have a line driver on, the hotter it's going to go, the more wattage it is. So for example, if you're going to go to 120 kilometers with the 800 gig ZR plus, then you're going to have a lot more wattage on that transceiver. Therefore, you need to be thinking about things like the OSFP, which runs cooler. So things to think about in terms of the form factor for 400 gig. And you'll have that choice between this for quite a while. OSFP, we think, is going to be a longer stretch because that's going to get us to 800 gig. Yes, 800 gig. We were going to show it towards the end of this year, but we pushed it out towards middle next year because of delays in manufacturing that we're all subjected to. But 800 gig is also in this new OSFP form factor, where QSFP-DD is going to be limited to 400 gig. So interesting form factors to think about here, okay? Now, why 400 gig, why 800 gig? What's happening in the industry to help us get through this in a very cost-effective way? Well, the cloud guys. So you've got your Amazons, you got your Googles, you got your Yahoos, all these guys are buying up 800 gig, 400 gig in mass. They're building out these big switches, a big infrastructure in mass. And we on the media entertainment side are taking advantage of that Moore's law, that cost efficiency that's happening. And if you notice right where we're at with that little yellow dotted line, that's that transition going from 100 gig is the norm to 400 gig is the norm. And then we'll see in another year or year and a half to 800 gig is the norm. And that's the economies of scale that you need in order to have that price point to enter into these higher bandwidths, to do the things that you want to do for UHD production, high frame rate production. Because if it's too expensive, you're just not going to do it. You'll stick with your SDI. This is what we want to do for you, is to have an industry that actually takes advantage of all these great price points. So you can buy a switch that's cost effective for what you're trying to do. Okay. Now we talk about other things in terms of the chip, and this might get a little geeky, but we want to introduce this because these are the things you kind of need to know from an infrastructure perspective, which is the transceivers and the fiber cabling itself. Now I know a lot of you guys are going to say, I'm out, don't care. I've got my fiber plant guys and they're going to take care of it. But what you may not know is the cost of the transceivers, or optics, as some people call them, is sometimes more expensive than the infrastructure of the switches themselves. So you want to carefully figure out what you want to do in a fiber plant. And that fiber plant could be a mix of both the 1 gig copper, the 10 gig, the 25 gig, 40 gig is kind of waning away, 100 gig and 400 gig. And choosing the right fiber plant is very, very important. We spend a lot of time talking about this with customers because you've got to do this right. You've got to plan this right. So the two things that you really want to focus in on is this dual LC, basically parallel. We plugged in the LC cables before, and then there's MTP12 or MPO12 connection. You might hear them called MTP12, MPO, MPO12, all kind of used interchangeably there. But if you look at the connector itself, it's got 12 sources of light in it. And what we're doing is using 4 lanes of that, the outer pairs, for our connections. And that's the least cost. And what we're doing with those 4 pairs is we're sending in basically a series of SerDes transmissions. So we're sending in 4 wavelengths at one time. So we're sending in, from a 40 gig perspective, 410, or 100 gig perspective, 425s. Now we get into the 400 gig, we're actually sending in 100 gig, but we're muxing that down. We're actually taking a 50 gig into 100 gig. We're actually converting it internally. But this is very, very important because this can make or break sometimes the installation. The easiest one to do is the LC connections for your 40 gig, your 100 gig, and even your 400 gig, because you can flip your polarity very easily. When you're dealing with an MPO 12, you can't easily just flip that polarity. So some things to think about as you think about your fiber plant and what to do. If you can do a short run, a home run, do an MTP 12. Okay, that's the most cost effective. When you're putting all those signals together in an LC, when you're muxing them, that becomes a lot more arduous, a lot more costly, if you will. So the cost of the transceivers go up because you're doing more on them. So, all right, well, you're making my head spin, Robert. Give me some ideas on how to actually pare this down, because you're telling me that this is, the costliest thing. My fiber infrastructure, my transceiver is the most costly investment I have over the switch. Well, here's the things: your data rate. What are you going to build for? Are you building for 100 gig, 25 gig, 400 gig? How big is big? What are you thinking for it in the future? Fiber type: single mode fiber versus multi-mode fiber. Now, this is something I'd like to get into a little bit more. Most people have like this OM4, OM3 multi-mode fiber plant today. You're going to probably have to get rid of that and start going to single mode fiber. And then also my reach, how big, if you have one facility, how big is that facility, or multiple studios or interbuilding? Interoperability with what you currently have as well. Do you have existing 100 gig that you want to move to 400 gig on? Do I want to do a split of 400 gig to 100 gig? And then my infrastructure itself, am I building out a new fiber plant or not? Now, I know, John, you had mentioned earlier about this wonderful adventure you went down with OM3 and OM4 with one installation that they wanted to keep their infrastructure, but in the end,
well, it is an important consideration for certain customers and certain applications. You have to appreciate the effort and labor cost of running the fiber in some buildings is really significant and sometimes outweighs all these other considerations. So the good news is the market does produce all kinds of optics. And the even better news is they all plug into the same SFP holes. So you can really engineer a system where you have the right optic for every different reach you need. So you have lots of ones that are AOC cables within a room. You have ones that are the sort of 2 kilometer single mode that can go anywhere in the building. And then if you have a few special cases where you have to reuse a piece of OM4 or OM3, there's an optic for that. And you get choices. And that's the beauty of the marketplace of these optics, is there's lots of people working on new optics and better optics every day. And it's to the benefit of all of us. And most of those optics vendors are only barely aware of the television industry. They're making them for the IT industry, who buys a lot of these optics.
A lot, quite a bit. I mean, thousands, hundreds of thousands at a time. So I mentioned this thing called a SerDes, and that's a lane. And currently on the chips, the network processors, we're working with what's called a 50 gig SerDes. That's the size of the lane. So you think of like a 400 gig, that's 8, 100 gig, that's 4. So you might hear things like SerDes and what we're doing from a transceiver perspective. And this is something to really note, because it's really getting back to what the cost is if you're taking these 50 gig SerDes and you want to go to 100 gig, the expense of the transceiver would go up. Now you have the flexibility, again, of changing the polarity. Instead of staying with the 50 gig SerDes or 25 gig SerDes, you're muxing that together on the transceiver. Now that's a cost to you, but that's a flexibility also to you. So these are the trade-offs that you need to think about. The other trade-off is, if I'm going to be going to 400 gig, then I want to be using the new transceiver types, the 100 gig DR, the 100 gig FR, and LR types. Previously, we had things like the CWM4 and the LR4 that were out there, and those are very cost-effective ways of doing this. But now that the industry has progressed forward, the new transceivers have come out, there's new opportunities to take advantage of doing things with 400 gig by 100, or 4 by 100 to 400 gig. So now you could take that 24 port 400 gig and split those out into 100 gig. Or you have a couple of ports for 400 gig for interfacility connections or OB truck connections, and I've got my 100 gig connections also on there too. So you have the flexibility or choice on these switches to go from 100 gig to 4 by 25, 40 gig to 4 by 10, 400 gig to 4x100. But you just have to pick the right transceiver to go from 400 gig, like the 400 gig DR4 for 500 meters, down to the 100 gig DR. Now, this might be a reference slide that you go back to, but these are the things you want to think about is what am I going to invest in now that'll give me my future-proof protection for my transceivers and cabling. Okay, so it gets a little dicey around what am I going to invest in for the future and what do I currently have? So here's a chart that says where are you at? It asks you where are you at, where do you want to be? Again, a lot of the answer is going to be, well, I want to be prepared for the future, and it's the same answer. It's going to be the QSFP, DR, FR, and LR that have been recently introduced. And that'll give me my introduction to not only my 400 gig, but my 100 gig capability. So now I'm back and forward, backwards and forward compatible. So those are things to think about in terms of transceiver. Again, very geeky kind of, it's facility focused, but it's definitely a cost factor. Now, if all this stuff is Greek, which for even a lot of networking people that I work with, it's information that they've never even thought about. Infrastructure, really? You can go to our Arista.com website. It's a great reference. I use it all the time. In fact, I used it before I was, here at Arista. There's a great 2 tabs in there: Arista.com products, transceivers. And you'll see in the by type, you'll see these different transceiver speeds, everything from 10 gig all the way to 400 gig. And you'll see the different acronyms, the CWDM4, the XD, you'll see all these acronyms associated with that particular transceiver type and the distance, and also if it's single mode or multi-mode fiber. And in the subsequent tab, the tab right next to it, you'll see the by type. And that's where you get into the LC connection, the MTP12, MPO12 connector. That's the one that's got the 12 across, okay? And you also see this thing called a DAC on an AOC cable. A DAC is that twin ax cable. So it's about as thick as your pinky. It's, and it's only bought in certain size, and active optical cables or fiber in the middle. I like the AOCs better than the DACs because, you can, if they're too long, then you can spin them around. You can actually coil them up a bit and tuck them away. Whereas DAC cables, not so much. The other thing with DAC, even though it runs at a lower, basically a lower wattage because it's going from electrical to electrical to electrical, it's not going the optical on that, is even though it runs at a good speed, like 100 gig and 400 gig, your distance is going to be limited. Also, the bend radius is not great. So if you need to close that door in the front, don't buy a DAC cable. And so I prefer to use AOC cables and things like that, quite frankly. And hopefully this stuff is things from a facility perspective, you guys are going, yep, that's exactly what we do. Lastly is single mode fiber. As we mentioned, single mode fiber is the way to go. It's evolving as well in terms of breakout cables, breakout connectors and things. So taking your 400 gig and going to 4/100s is a thing that people do all the time. But there's the new connector called an SN connector. And instead of having an external breakout cassette, it's a breakout on the 400 gig transceiver itself. So remember that 24-port switch where you could put these SN connector 400 gigs on them and go native 100 gig right off of it. So now you don't need that extra 1 RU for breakout cassettes anymore, which is a great idea. It also gives you that economies of scale. Okay, there's also the things to think about too is this duplex. You'll see 200 gig have a pop for a while. It'll come out in more storage type of solutions. That you'll see coming out here next year. So you will be ready from 400 gig to 200 gig. You might see these on some high-end vision mixers, but again, it's going to be a pop for that transition from 100 gig to 400 gig. They'll come out less expensive than the 400 gig to start off with, but then you'll see the 400 gig transceiver costs come down as well, okay? The last thing to consider is multi-mode fiber. And my advice is don't walk to single mode fiber away from multi-mode fiber. There are some challenges in here. You'll notice that this one right here, a multi-mode fiber for 400 gig is an MPO 16. So that's a different connector than the MPO 12. And the other thing is it's cut a little bit differently. You'll see this thing called it's an angled multi-mode fiber. So it's not that flush. So something to think about if you're going to go for short runs, maybe in the cabinet or end of row or something, you can use this. But I'd prefer that you stuck with something that was standardized on a single mode fiber infrastructure than a multi-mode fiber infrastructure, even though it might cost a little bit more. That way you have this this ability to mix and match things, this ability to have sparing, and also the ability to say, okay, I've got extras right here, so I can go ahead and use those. And lastly, this is one of the things that I want you to consider for large facilities, or maybe between OB trucks or something in the future, is we have this 400 gig ZR OSFP connector here, and then we have this ability to mux 8 channels of 400 gig. 8 channels of 400 gig muxed onto a single fiber pair. Holy smokes. Now you no longer have to run a lot of fiber between locations, single fiber. You're muxing them together with this power sucking alien, so to speak, of this optical line side system. And you can see it right here. You've got the LC connector, and then you've got the client connector. You've got the client connector that goes across, I'm sorry, the line connector that goes across, and the client connector that goes here. So now with a single pair of fiber, you can get terabytes of data between facilities. So yes, 400 gig, 800 gig in the future, terabytes of data, all with the infrastructure. And if you have more questions about all this stuff, please come to us. And by the way, there's a plethora, as John said, there's a plethora of transceiver types and all kinds of things. You can get lost in the weeds. This is why we spend a lot of time, us on the networking side of things, to understand and ask you questions about what's your fiber plant? What are you going to connect to? Where are these devices? Like, for example, the S&Ps that have 200 gigs on them. What's the right distance on them? Are you going to use AOC cables? Are you going to use standard transceivers? Are you going to patch into something else? Do you have a fiber facility that's already built? So we ask a lot of questions about that because we want to make sure that you have the right solution at the right price, at the right distance, to make sure that you're successful not only in your journey to UHD, HDR, HFR, but also from an infrastructure perspective, that you're good to go with this and you have a solution that is built for speed. So that was a lot in a short amount of time. So John, you want to wrap us up here and tell us what we just talked about?
Sure. I mean, we covered a lot. So if you set your clock back an hour, we started talking about formats and pixels and UHD and HDR. And all those things in some way require flexibility that was just hard to achieve in SDI. That's part of what drives us to IP. And when you're doing UHD or even 8K, of course, it just drives how many bits are going to fit on the wire. Also works in the favor of the IP systems. And then there's a lot of production considerations about doing that conjoint production. But all to say, the IT industry is ahead of us on this, meaning that the switch ports and switch port speeds and link speeds, it's the smallest 400 gig switches you can buy are bigger than the largest SDI routers that were ever built in terms of bandwidth through. So we're really in a good position with respect to the relationship between television engineering and the IT technology that we can leverage, that we're not shopping on the top shelf. We're shopping on the middle shelf of the available options from the IT providers in terms of the switch ports and optics and things we can use. The other beauty that we've just spent some time talking about is the plethora of choices on the optics and on the link speeds and link accommodations. It really is a great marketplace of options for the optical reaches and what you can get on a fiber. I especially like the new optical mux stuff that really packages up the WDM and makes a very reasonable system that can go quite long distances.
Yeah, thanks, John. That was good. So there was, did we get any questions from the panel?
We've answered a lot of questions. So
pretty much we're answering all the, yeah, we're pretty much answering all the questions as we're coming in. We're getting lots of good questions coming in.
Yeah, there was a question about 800 gig, Robert. What's the state of the world on 800 gig?
Well, I will
off the top of your head.
Yes, we had a slide on this, but we were told not to show it. But it has been demonstrated. 800 gig has been demonstrated at the OFC conference. We showed a very large switch that's coming out from Broadcom, showing 800 gig ports, somewhere in the neighborhood of, I think, 24 ports of 800 gig. Again, that's using, the SerDes lanes of about 50 gig, and we're going to go to 100 gig SerDes. So 800 gig will come out. In fact, rolling back to the slide back here, will come out as a multi-lane, as we jump to it, multi-lane 800, 400, like a 400 gig is today. And then when we get to the 100 gig SerDes, then you'll see it really become economies of scale. So we're going to have a nice little bump here towards the end of the year. We were going to announce this year, 2021, but that'll be announced probably mid next year, just because of basically manufacturing constraints. But it is here in labs. And in several cloud providers as well.
Right. So from a technology perspective, 800 gig is, doable, and now it's just the logistics of production and execution.
Yeah, and then the transceivers and catching up with all the different transceiver types that are out there.
Right, but I think from a television industry perspective, 400 is going to hold us for a while, and I think the biggest use case of 400s is really going to be that DRFR kind of breakout to multiple 100s at the other end, where things like the Sony and Grass switchers and other switchers now are all sprouting 100 gig ports, and so that way they just tie directly to the core and use the 400 gig DR kind of breakouts. And the same thing with our bulk processors. The 100 gig on our end goes to a quarter of the 400 gig on the other end, builds a nice tight system.
It's it's interesting you mentioned that, because those are the what I call gravity effects. You've got your multiviewers, you got your mixers, and everything's going to be 100 gig, and those things you have to plan for up front. And if you're really going to think about where 100 gig is, you want to bring everything to that. That's why, quite frankly, if you have this distributed facility with different studios and different vision mixers, bring them all to a core. Stretch that fiber all the way to a single switch, whether it be like something like this or a much bigger switch. Put your SNPs all the way to the core, because you're going to get the fastest processing. It really is just a fiber plant thing rather than anything else. Any other questions from the panelists? I think there was one that came in about the MPO connectors. I'll just hit that real quick. Again, kind of a dry thing, but it is what it is. You'll hear these things called type A, B, and C for the MTP12 or MPO12 connectors. There's a polarity. If you remember back in the RS-232, 422 days, is you got transmit, receive, just like right here with the LCs. Well, you have this law of odd numbers when you patch your MPOs together. You need to flip, and then flip again. Can you do it with the MPO12 connectors? Yes, but you have this odd thing because you want to keep your pigtails type B at the end on each one. So if you go B, B, and B, you'll be okay. But remember, that's 12 fibers are really 8 fibers in use, and you want to make sure you get your polarity right on there. We see a lot of people trying to save money, trying to do this from a fiber plant perspective, and end up going with something that puts them on a pair of fibers, because you can easily change that polarity. Okay. Any other questions from the panel? How are we doing?
Actually, we've got a steady stream of questions coming in right now.
Yeah, I think we've ground through most of the questions in the chat, so some are detailed. There are questions about the addressing architecture and when to use layer 2, when to use layer 3, and so forth. There's a well-known challenge in multicast about address aliasing, and that 239.0.0.0 and 239.128.0.0 actually have the same MAC address, and this causes no end of grief if you are trying to do a layer 2 kind of network where all the ports are on the same VLAN, all the ports are in the same VLAN. And that's not that's across switch vendors. There's lots of challenges with this. The best practice is to make each switch port its own little tiny VLAN. That's what we're doing in just about every install that we do anymore. And that way it works around that whole question about MAC address aliasing and so forth, and lets layer 3 do the work. And that's supported by the usual switches from all the switch vendors. It's there aren't that many things that Arista and Cisco agree on, but this is one of them.
It's part of the standard. The other thing to consider too, I mean, maybe this is a whole other webinar, is do I need layer 2 to begin with? And of course, if you're dealing with something like Dante that does, PTP version 1 and also does the registration discovery services, handing out IP addresses and stuff, that's where basically your layer 2 stretch will have to come into play. But those are more conversations than it is, here's the only way to do it. And then also unifying your plant too is PTP wise. How do you convert that PTP version 1 on a Dante environment to a version 2? Well, there's something called Dante Domain Manager and the newer chipsets that go along with that. So really good architectural conversations to be had.
Mm-hmm. Okay, well, I think we're
done.
Sort of working it through.
All right, we'll hang out for a few more minutes.
So
just
someone mentioned the multi-mode of the multi-pair optics, and that's what we're talking about, the OM3 and OM4 multi-pair optics. There are SFPs to support that, but as you get into the 25 gig or even 50 gig lanes and the, so forth, the reach of the OM3s and OM4s is getting smaller and smaller. So you, even with the best optics, the fanciest like the XSR4s and things, the OM4 range is, what is it? It's like 200 meters or 300 meters.
Yeah, it's about a couple hundred meters. It's not, and that's the whole thing of it, because you're putting, like you said, more bits on the wire, so to speak, and more bits on the fiber. And you have other things like dispersion, dB loss, things like that to consider too. So if you're forcing it down on multi-mode, you've got a lot of refraction that's occurring on it. Whereas single mode, it's a lot cleaner light. And so you can go farther distances.
Right.
And then you don't have to worry about things like.
Right. And that said, they're both longer reach than 12 gig SDI.
Yes. Easier to terminate too, I'd say. And easier to connect in.
Yep. Well, you have to have the right tool in either case.
Don't use my nubby fingers to connect in there.
All right. No, I think we've hit a lot of the points. We've hit a lot of the questions. There's still a few coming in. We'll make sure we answer all of them as we go.
Okay. With that, remember this is the third session. All of them are recorded. For those people who have registered for these events, you'll get the notification of the recording, which will be out here about a week. The 2 recordings for session 1 and session 2 are available. So again, those that have registered for these sessions, and you just register once, you get all 3 available. And then we have those prior ones available to you too. Just ping any one of us and we'll be able to get back to you. Or you can remember the slide, if you can roll this back in the video to see what those YouTube links are. No more strip and crimp. Thanks, everybody. Yes. Thanks so much, Alan. Appreciate that. Yes. All right. With that, thanks so much, everybody. Appreciate your time. And for Lee, if we could bring you back, and Mike, if we could bring you back, just want to say thank you so much. Again, this is the 3rd part of this, and thank you to John very much for co-presenting with me. Lee, fabulous job last week on PTP, and Mike for kicking us off. He took the high road. He chose the short straw on doing the first presentation on monitoring. Any last words from anybody?
Well, it's been great fun. Thanks again.
Hopefully everyone learns some stuff.
Yep. If you have a hankering to hear more about 2110 or NMOS or some other things, don't forget the Ames IP Oktoberfest, which is happening, oddly enough, today and tomorrow.
Okay. With that, thanks so much, everybody. Appreciate it. Have a great day.